Hey everybody, welcome back. Good to see you again. Mr. Smith here. As we've been talking about, energy conservation means that energy can get converted from one form to another form. And what we've done so far is to concentrate on situations where energy losses to friction don't play a role. In real life, that's a little bit of an oversimplification. And I'll give you a simple example of something. Let's say you do some work on a box. You push it across the floor because you're helping somebody move into a new apartment or something. So, what's going on here is that your body digests the chemical energy in food and enables you to do work. So, that work turns into the kinetic energy of the box. But in real life, if you did 100 joules worth of work, you don't end up with 100 joules worth of kinetic energy. In reality, you might end up with nothing if you push the box across the floor and the box stops. So where does all that missing work go? It really doesn't disappear. So what I wanted to emphasize is this energy conservation idea really works. Energy doesn't just go missing. What happens instead is now in this modern time, we understand that missing work, the change in work that's gone absent without leave, really is a form of heat. It turns into thermal energy. And we know now that thermal energy is really just the jostling of molecules. So what's happened is you push a box across the floor is just you've warmed up the floor a little bit. You've warmed up the box a little bit. And what does that mean is that the molecules inside the box and inside the floor really are jostling a little bit differently than they did before you did the work. Okay? So the way this plays out in physics isn't going to be a tricky thing for you. You should be able to use it to put together all of the ideas we've been talking about. Conservation of energy and work equals force times distance. And I'll show you an example right now. So a classic situation where you don't get pure conservation of energy would be a thing like a water ride. So let's just take a look at a quick example right now. So you can see in the video, people at the top slide down the initial tube, they ride up the wave portion of the Kari, and then they roll down to the bottom. Okay, and the whole thing is a really short ride, but it's very popular. And what I want to do on the next slide is just work out standard conservation of energy problem and see what we learn. So this is a top to bottom kind of ride, high to low. So what we're going to do is just set up our PE and KE like we do on our diagram, and it's going to swoop down here and it's going to become PE and KE at the bottom. And let's just go start from the top. So 10.7 meter high, 75 kilograms, we can work with that. So we've got some PE at the top, mgh, and acceleration of gravity, 10 meters per second squared, 10.7 meters, and all of that turns out to be 8,025 joules. Okay. Now, in an easy problem, the person will have no speed. Well, this is actually what happens if you watch the video. The person really does start with no speed. They start from rest and they just scoot down the hill like that. Okay, so that's nice. Second thing that happens, they also make this easy because there's not a final height. The final height is 0, so we know that the final PE is going to turn out to be 0. Here's the difference. Rather than just assume like we've been doing that 8,025 plus 0 automatically shows up down here. And if you're good at this, you would have just penciled in 8,025 for these easier questions. Notice that they give you an actual speed. So at the bottom, the 75 kilogram rider is moving at 10 meters per second. So I need to use that. So 1/2 of 75 kgs and 10 meters per second. Don't forget to square that. And we get 3750, I can just fit it in there, joules. Okay, so here's the thing. 3750 doesn't equal 8025. So what's happened? It's really easy to deal with. Keep in mind that energy really doesn't go missing. What we need to do is just open up one more slot in our brain or one more slot in our organization to allow for that reality to happen. So that new slot's going to be called friction. So the friction is just the missing energy. So really, there is 8,025 joules at the top. There really is 8,025 joules at the bottom, guaranteed. Where did it go? The missing stuff went to friction. So I'm sure you could figure out how to get that. You just subtract 3750 from this number right here. And what did I get? The missing energy is 4275 joules. Okay? And that's how you do it. So let's just check out one more example that's got a little extra feature added to it. And rather than show you a video for this one, if you want to go ahead and get on YouTube, definitely go ahead. If you haven't seen this, it's nuts. So Zorb is kind of a fringy sport that started in New Zealand where people would roll other people down hills in huge inflatable like silicone plastic balls. Okay, they're big, heavy, they have a ton of friction, which is really important. Otherwise, they'd be deadly because people would just get so much speed going down these hills. Here's how you do it. Same kind of situation. We're going to read it. Zorb goes from a 20-meter high hill at a speed of 2 meters per second. How much energy is lost to friction at the bottom? 5 meters per second. Okay, so same. It's an up to down problem. So KE and PE. And we're going to set up the same thing down here, PE and KE. And notice as we do this first part, 160 kgs, this is pretty standard. So just put in the first height, 10 meters per second squared, and 20 meters high. And that's a lot. So 32,000 joules. But here's the thing I was going to say. Notice this next part. They actually give us a speed here. So you have to use it. So 1/2 mv squared. So 160 kgs full of ball plus person. And 2 meters per second. Got to remember to square it. So it's 4 times 1/2 times 160 turns out to be 320 joules. So the total energy going into the problem is 32,320, right? Add them together, okay? Now, what's also nice is this one, they give us 0 joules at the bottom because there's no height. And again, just like they did before, they do give us a speed, so 5 meters per second. So I'm going to use that, 1/2, 160 kgs, plug in my 5 meters per second, and I'm going to remember to square it, and I get the whopping sum of 2,000. So 2,000 joules. That's a lot that went missing, right? Okay, so we had 32,320 in the beginning, ended up with just 2,000. There's a lot that's in that missing category. Again, not hard to figure it out. What's missing is just 30,320. So just the beginning energy minus what we know we had, and that's it. Now, what you're going to see me do finally is just wrap the idea of work into this. Friction can do work. So it has force, it has distance, and if you think about it, the force and distance are opposite each other, and what's going to happen is this work that's done by friction is going to be negative. What I'm going to do is just use that right here. Work equals force times distance. I'm not going to get hung up on the negative sign this time, but what I am going to say is that we know that the work that's been done by friction is just the missing energy, 30,320 joules. We know the distance, well, the distance is going to be the length of the Zorb run. So that's 250 meters. And we can solve this very easily and figure out the force of friction that was acting. So work over distance, 30,320 joules over 250 meters. And there you go. Turns out to be just 121.3 newtons is your average force of friction, okay? So there you go. So conservation of energy still works. We just need a new category to put it in. Missing work or missing energy goes into the form of friction, okay? So that's it. Bring questions to class. Great to see you. Have a good day out there. Take care. Bye-bye.